So my talk is about distributed FPGA number crunching for the masses. What a title. So let's start with the number crunching part of it. So it's a valid question to ask, who's still doing number crunching these days? I mean, breaking keys is nice, but hasn't everybody moved to 128-bit encryption now, AES and so on? Yeah, most stuff has moved, but it turns out there's plenty of stuff that's still unsolved, that has been encrypted with like DES, and where we still don't know the key. And there are some interesting things to work on that still require number crunching action. So DES, of course, as I said, is a classic example of brute forcing keys. People have done that. It's a 56-bit key space, so it's manageable. There are some synthetic problems, like the N-Queens problem. People are trying to solve this using FPGAs. The distributed net OGR project, and a couple of other things. But for talk, let's focus on a real-world example. So this device is a Triforce arcade machine. It's something that's hidden in an arcade cabinet in the end. So this is where the actual game is working on. It's a modified GameCube. It doesn't matter so much. So inside this thing, there's also a dedicated processor that's doing security stuff and some management stuff and so on. And a certain version of these Triforces have a thing called, so the games have been dumped and emulated. You can run them in an emulator today, similar to MAME. It's a different emulator, but it works. But there's still one unsolved mystery. And if we look closer, one of the files that run on this machine is a file called firmware.asic, and it's obviously encrypted if you look at it. And so far, nobody really knows what this file is supposed to do. We know it's some kind of a firmware, and we know about what it's supposed to do, but it's encrypted, so we can't really do much here. If you look a little bit closer, you see this repeating 8-byte patterns. That's actually a pretty strong indication that they're using a non-chaining 8-byte block cipher that will produce the same ciphertext for a given 8-byte plaintext, and it will repeat that ciphertext if you encrypt repeated copy of the plaintext. And for this Triforce thing, I don't want to go into the details so much, but we know that the games are encrypted using DES. So the idea is, well, they have a DES hardware, maybe the firmware is encrypted using DES as well. So this was kind of the starting point. I wanted to get this firmware because I'm interested in it. There's no real gain, but I mean, it's a mystery, and I want to solve that mystery. So if we look at the firmware file, do a histogram of 8-byte blocks and sort them, we see that there are some duplicate blocks, but there are two distinct ciphertexts that are repeated a lot more often than the other ones. And so the assumption here is that either of these plaintexts encrypt to all 0 or all FF, because that's a pretty popular pattern in a random binary that's executed. So yeah, the assumption is that any of those two will decrypt to all 0. Let's call them C1 and C2. We don't know which one is what. We only know that they both occur magnitude more often than any other ciphertext in the binary. There's one particular thing here. The Triforce games are actually DS encrypted, as said, but they are also byte reversed before and after the encryption. So we have to keep this in mind. If we're brute forcing for a key, we want to be sure that we are looking for the correct ciphertext, because otherwise we might miss it because it's byte wrapped. So we want to take into account that they might be reversed as well. So another interesting thing about DES is the complementation property. It means that if you invert the plaintext and you invert the key, you get an inverted ciphertext. This doesn't sound so interesting, but for brute forcing, it's actually very interesting, because if we have the ciphertext of an all FF, and we invert that ciphertext, and we can find a key that encrypts all 0 into this inverted ciphertext. The key will be actually the invert of the real key. So it's written down here. This basically means that we can cut the time to brute force to half the time, because it saves us 1 bit. We are equally likely to find the inverted key and the non-inverted key. So we can find either of them, and then we just invert it if it's the wrong one. So it's something to keep in mind. So to formulate our goal for breaking this mystery, we have two plaintext. They might be reversed, so we will also look for an inverted version or byte reversed version of this. Awesome, thanks. And we will, for both plaintext, for both ciphertext, obviously, we will also look for the inverted version because of this des property. And our assumption was that it is an all zero plaintext. So what we will do is to encrypt 0 with all possible keys until we find any of these 8-byte patterns. And if we found any key that encrypts zeros into any of these values, we're pretty likely that we have found the key. So that's our goal. Yeah, DES, probably everybody knows this, but it's a block cipher based on the Feistel scheme. So it does this. It has 16 rounds, so it always uses half of the previous round output and uses a round function on it, and then XORs it with the remaining half from the last round. It's 16 rounds. This is how a round looks like. The only real work here are the S boxes. There are 8 S boxes with a 6-bit input, 4-bit output, and this is really the element of DES that requires the most work, regardless if you do this in software or in hardware. S boxes, yeah, if you're implementing DES on a CPU, you could use a lookup table for the S boxes. But there's a much more efficient way, which is called bit slicing. It basically means that you're breaking up your S boxes from being, it's not anymore a lookup table, but you break it up into logical operations. And the nice thing about logical operations is you can run them on 128 bits in parallel if you have a vector unit, which most CPUs have. So the way to go for ALU-based architectures, so that includes CPUs, that includes GPUs, that includes SPUs on the cell, is to do bit slicing. And it's on a traditional Intel CPU, like on a real high-end machine, you get about 64 million keys per second that you can try, or on a 6-core machine, 6 times that value, which is 384 million keys per second on a real high-end machine. So this is not a random machine that's standing somewhere that you want to recycle. This is a high-end machine that you would buy today. So this is our key space, 56 bits. And 384 million keys per second means that in 1 second we can walk 28.5 bits. This is, okay, so of course this is logarithmic, so it doesn't mean in 1 second we have half the key space. It means that, well, we still need the remaining 27.5, 2 to the power of 27.5 times this second. So a day has 2 to the power of 16.4 seconds. It's interesting to say it this way because you can just add them up. So you know that you will get 44.9 bits done a day. And if we just leave it running until we reach the end of the key space, it requires us 6 years to walk the entire key space. And that's on a high-end machine today with a 100% duty cycle running 24/7. So 6 years, I don't know, I'm interested in that key now, and I want it in a week and not in 6 years. So just leaving it running for a week, there's still we won't walk the entire key space in a week, obviously. But we can just use more machines. So we can use 313 machines approximately. And then we will get our key in a week, which is still not what I want to do. Yeah, so the cell, everybody knows about the cell and the PlayStation and so on. So the cell SPU can evaluate 128 S-box lookups in 40 instructions using this bit slicing technology. It's equivalent to 64 cycles per key or 50 million keys per second at 3.2 gigahertz, which is about 300 million keys per second per PS3, or actually 350 thanks to Marken. So it's about as fast as a high-end machine. So it's still not gaining us so much. We could buy 300 PlayStations or 300 PCs. I'm not sure what the better deal. Okay, GPUs. People are telling me GPUs are fast. They have like many cores working in parallel. There's a problem. Everybody's using GPUs for MD5 and SHA-1. But these are actually, MD5 and SHA-1 are actually optimized to run on ALU-based systems, like on a CPU. DES is optimized to run in hardware because when it was designed, there was only hardware to run it in. So DES is not really suited well for GPUs. You could do the bit slicing thing again. We can estimate it to it's about 10 times as fast as on a single CPU core, like on this high-end CPU core. It would be 640 million keys per second, or 29 or 2 bits. It still takes a while. So if we put it up here, for the PC, it would cost 313 devices, $150,000 about, if we calculate $500 per node. For the PS3, it's a little bit better. It's only $93,000, but you still need a hack because Sony removed that other OS feature, and you would have to pay a hacker to do the hack, and you would have to pay a lawyer if Sony comes back, and we don't want that. So the GPU approach is much nicer already because we can use one PC and stick in a number of high-end cards, and we can estimate it to be like $45,000, but it's still too much. That's not what I want to pay for solving this mystery. Obviously, there's one item missing, which is FPGAs, which is this talk about. So let's see what FPGAs can do. On an FPGA, first you basically have the choice to implement a pipeline design, which means that you unroll the DES into the 16 DES rounds, so they will all exist in parallel on the chip, and that gives you one encryption per cycle after an initial latency. But it's also 16 times as big as using a space-optimized design, which only implements one instance of the round function and uses the 16 times. It evens out, but actually on an FPGA, a non-pipeline design is less efficient because there's some logic around the round function that you would have to replicate more often. So actually going for the unrolled design is a much better choice here. If we can fit about 1 to 10 pipeline DES designs in a single FPGA, depending on the FPGA size, depending on the FPGA, we can run them from 100 to 200 megahertz, which doesn't sound so crazy, but we will get one key per cycle, which is much better than what a CPU, a GPU, or SPU is able to do. So that gives us in the order of 100 to 2,000 million keys per second already. So for 1 week, I still need 60 of the big FPGAs or 1,200 of the tiny ones. So here's our key space again. Here, if we take a high-end PC, we get that many keys per second. Then if we scale this up for a year, we're still not done with the key space. So what Distributed Net was doing back then when they cracked DES was they had a distributed client you can run on your machine, and the largest or the peak connection or peak contributor count, I should say, was about 25,800 users that are working on a DES project at the same time. Obviously, those were not using PCs as we have today. Like this high-end PC didn't exist back then. So if you would have 25,000 of these high-end PCs, it wouldn't even take a day to break this. It would take much less. But that's not an option because you won't get 25,000 gamers to work on your project and not play games anymore. So that's not an option, unfortunately. Using an FPGA gives us a slight improvement in the rate, but that's not so much the main point. So if we, again, target for the week, it will still not work. It will not work with 16 FPGAs, but it will work with 256 FPGAs. So it's much better already than the high-end PC. So people built that. It's called, it's looking like this, or this was actually a prototype of it. It's called Copacabana, the cost-optimized parallel code breaker. I think it's a pretty cool name, actually. And so it wasn't my idea, of course. So this was a project that university designed in 2006. Their hardware required 12.8 days to walk the entire key space. They used 120 Spartan 3 FPGAs. It turned out that at last back then, but it's probably still true today, the Spartan 3 at this size is about the best logic per price you could get. So it's only $4,200 in FPGAs if you do it that way. if you look at the list price, you might get them cheaper. If you talk to Xilinx, you might even get them more cheaper. But it's still cool, but I still don't want to pay $4,200 for the keys. Much better than what we had before, but it's still too much. So my goal was to not spend more than $1,000 on it. And yeah, I looked around and tried to use FPGAs from different vendors or different FPGAs, and it didn't work out. The cheapest thing was about as expensive as this Copacabana thing. So using new parts, it just didn't work. So that's when I came up with eBay. If you search for FPGA and for chip recovery, you will find some weird stuff. You will find boards that have been pulled out of, let's say, 3D base stations or network equipment or whatever, video processing, and there's usually no documentation on them, or there are usually not even decent pictures. Probably they just say what chips are on there, and they have no clue what this is about. You can be happy if they don't destroy the board, because what they believe that what people want to do is to desolder the BGA chip, reball it, and then use it again. Which kind of makes sense when an FPGA costs about $2,000, but these chips are usually a few years old, and I wouldn't want to build some project that requires a $2,000 FPGA based on used hardware if I have to deploy it. So I'm not quite sure what they want to do. But anyway, if you do this, you will find very interesting stuff. It's kind of hit or miss what you get, right? Because you don't know what you're buying. So what I bought was this. This was the picture I got, or about the picture. It says exactly nothing, except that this is a PCB with a Xilinx Vertex 2 Pro on it. So the item description was 3 Xilinx Vertex 2 Pro on PC board. Yeah, that's true, but it doesn't say much. Anyway, I bought them. They were cheap. The Vertex 2 Pro in question, if we look up the list price today, I mean, this FPGA is from 2006 about, or 2005. If we look up the list price today, it is a whopping $2,000 per piece still, if you buy them new. And we just paid $50 for 3 of them, which is a much better deal. Obviously, they are end of life, so the list price doesn't really reflect the value of that chip, but it's still not a bad deal. So if you compare this with modern FPGAs, you won't get that logic capacity of that chip anywhere near $50. That's just impossible. You would still pay, maybe not $2,000, but maybe $1,000. The good thing is I bought 3 boards of those, and the remaining about 50, or we're not quite sure how many they actually are because of some logistic problems, of these boards have been obtained and they are in good hands. And the plan is to bring them up and make people use them for projects, which is not so easy because you cannot just compile stuff for it. But that's why I'm holding this talk, to make it easier. So the plan is to bring them up and use them for interesting projects. If you have an unknown board, say you bought one of these boards from eBay and you want to use them, the first thing we need to do is to find power. We need to power up the board. And if you're lucky, it's just a single voltage. If you're not so lucky, it has multiple voltages or even the power sequence requirements. So let's hope it just requires a single voltage and has the regulators on board. The next thing, we need to talk to the FPGA, so we need to find JTAG, which is this standard which is the way how you talk to FPGAs. It's like 4 dedicated pins, and you can program the FPGA. We'll come to that later. If you have JTAG, you can program a bit stream into the FPGA. But you still need to do something. So what you need is a clock. And of course, these boards usually have clocks. I mean, they are hopefully still working. So, but you have to find them the right pin on the FPGA. So power, so this is the board, by the way, that I got. It's some 10 gigabit Ethernet network something. I have no clue what this really is, but it has a 10 gigabit Ethernet switch on it, the Broadcom chip on the left, and it had an optical transceiver on the right, which is missing. And in the middle, you can see the 3 big fat FPGAs. So to power this up, this is the power connector. There are 2 of them, actually, but they are wired in parallel. So finding ground is easy. You just find another ground and use the continuity checker. Then the next 2 pins, or one of them, is probably the high power input voltage. Getting the right voltage is not so easy. So what you should do is to check the regulator setup, check how the power supply on the board is working, check the data sheets of the chips for the maximum ratings, check capacitors for the maximum rating, so you at last know a maximum value that you should never exceed. Getting the real value, I mean, they could use like 25 volt rated capacitors and still only require 5 volts. Try applying 5 volts, and if nothing happens and if it doesn't draw any power, crank it up. Be careful, you don't want to destroy a board, but you probably don't have to destroy a board. It's usually possible to figure this out without destroying a board. I mean, we have enough of these boards, so it wouldn't be so much a problem, but it would still be a pity. So we found out that it requires 12 volts, which is great because 12 volts, there are already made power supplies for 12 volts, so it's great. There was a third pin here. If you look into the power connector, I don't have a photo here, but it's a little bit shorter. And that indicates that this is meant for hot plug operation, when you plug this board into a backplane, so that one of the pins get power the last. So it turns out this is actually a 12 volt sense pin, or a power good pin. So if you just wire them up in parallel to the 12 volts, you'll be fine. So once you do that, it will at last, an LED will go on, which is some sign of life, and the power current, or the current is in a reasonable range, so everything seems fine. Of course, the board is not doing anything. Okay, so we found power, and the next thing is to find JTAG. You can be lucky and you can be unlucky. In this case, so first JTAG, we are looking here for 4 pins. TDO is an output from the FPGA to the JTAG header. Since people developing for FPGAs need JTAG for programming the FPGA and debugging, usually all of these boards still have a decent JTAG header. The pinout might be different each time, but the chances are pretty big that there's still a JTAG header on the thing. So TDO is an output from the FPGA. TDI, TCK, TMS are inputs into the FPGA. The FPGAs can actually be chained together, so the TDO of one FPGA will go into the TDI of the next FPGA, and then you have them all in a chain, which is convenient. Anyway, we're looking for these signals and, of course, ground. So we are looking for a header that has these 4 signals and ground. This is the backside of the FPGA on these boards. So it's really nice, and it's pretty uncommon, actually. They have a via for each of the ball of the FPGA. So it's a 1152 ball package, but they have a via for all of the boards. So you can access all of them, which is great. And what's even better is that they marked they numbered the vias on the edge. So it's a little bit hard to see, but you can see that it has the numbers of the columns, and it also has the rows. So that's very convenient on this board. So you can access any pin. So what we just do, we look up in the data sheet where the TCK, TDI, TDO, TMS pins are. We locate the via, using cross-checking simply, so it's simple. But then we have to trace the via, and this is I think an 8-layer board or something, or 12-layer board. It's pretty thick. So it's pretty hard to trace a signal. The trick here is to use tinfoil. You use a continuity checker. You connect one end to the pin you want to find. You connect the other end to tinfoil, and then you just push the tinfoil on the board. And if it beeps, you know that somewhere in this area Of course, people will tell you to never do this because continuity checker applies voltage to that and ESD and everything. The truth is, I never destroyed a board using that. You might be unlucky, but still, it's, I think, the way to go. You can then, if you know the approximate range, you could, make your tinfoil a bit smaller to reduce the area, and finally try each signal you can find. We did this. So here's TCK. You can find the via pretty easily. We found this header, the picture is actually broken. One of them is TMS. Anyway, so we found a 6-pin header with ground, the JTAG signals, and a voltage sense. Be careful because FPGAs usually run at a low voltage, or at least the core runs at a low voltage, and it might be less than 3.3 volts. So if you use JTAG, be careful to use the correct levels. In this case, it's 2.5 volt. So that's why the voltage sense is there. So the better JTAG adapters use this pin to control their output voltage. Okay, so we found JTAG. We still need to find clocks. JTAG also allows you to do a thing called boundary scan, which basically means you can query the digital value of each pin. There are some tools. This is a random tool, but there are more tools. You can even write this yourself. It's pretty simple, actually, that display the state of the whole chip in real time. So if a pin toggles, you will see this, that it will go from red to green or the other way around. And it will also display you what pins changed. So if you find a pin that changed all the time, it's pretty likely a clock pin. You can use a scope to verify that. So that's one way to find clock pins. The other way is FPGAs usually have dedicated clock pins that have better routing across the whole chip. So they're global clock pins, GCK for Xilinx, but all other FPGAs have them as well. So just look up the data sheet, look for the dedicated clock inputs. There are 8, I think, on this FPGA, and just scope them or write something on the FPGA that blinks an LED or something clocked from this clock. So finding the clock pins is usually not so much the problem. And I found a nice 155 megahertz clock, so that's great to go. So we have the clocks. Let's see what we can do. So if you do the math, you need about 20 boards of these to get it in 1 week. So 20 times 50 is about 1K, which is coincidentally exactly the value I wanted to spend on this project, which is already a great start. So if we add the table, the FPGA to the table, we will see that for 1K we can get the equivalent power of, well, what was too expensive before, based on recycled FPGA hardware. Okay, so for the implementation, remember I still want to find the zeros that encrypt to any of the 8-byte blocks. So what I was doing is to take multiple DES cores in one FPGA that all encrypt the same all zero plain text. It's actually selectable, but it's all zero for this, and match it against multiple patterns. Because if we want to find multiple keys that all have the same plain text, we can do this in one run to the key space. We don't have to run the key space twice. So put them all into the table and match for multiple patterns. That's much easier than running the key space, working the key space once for each of the patterns. The way I've implemented this is that each core searches the key space segment. The lower bits will be identical for all DES cores by a single counter in the FPGA, and the upper bits are the work unit. So here we have the zeros, we have the key. We see that the right part of the key is identical for each of the DES cores. This is a 40-bit count in this case, so I broke it up after 16 bits, for example. And the work unit is the upper 16-bit of the key. So each DES core searches a separate segment, and that's why each DES core produces different ciphertext. We then have to match these ciphertext against all the patterns we have. And and we actually see in this prepared example that there's a match, which is pretty uncommon, of course, because most of the time it won't match any of those. So if it finds a match, it will stop the FPGA and wait for the host to collect the result. To get a sense of the numbers, if we have 8 cores at 200 megahertz and with 16 patterns, we're generating 12.8 gigabytes per second encrypted data per FPGA. And we will match that 12.8 gigabytes against 16 ciphertexts in parallel, which means that we have 204 gigabytes per second. Then we need to compare, which is pretty massive. And also explains why PC has so much trouble in getting decent rates at DS cracking. The naive approach for the matcher that matches up the DES results against the patterns is to have 8-byte registers implemented in FPGA logic, have 8 times 16 compare units. This is all for 16 patterns because I had some more keys I wanted to brute force, some test keys to make sure that it's working. If you implement it this way, it will already take about 1/4 of the whole FPGA just for the matcher. A better approach is to use the thing called content addressable memory. It's like normal memory, except you don't supply an address and get the data, but you supply data and get an address, or actually a match mask. For Xilinx, you can use BRAMs to implement this, but it's not real content addressable memory, it's more a bit mask. So you have, for example, if you want to match 8-bit word, so 1 byte of the pattern, you have 256 entries with 64-bit each, and then you have, if you want to look for 64 results. So it looks like a waste at the first sight, because real content addressable memory only had like the number of patterns entries, but that's not how it works on Xilinx. It looks like a waste, but the great thing is once we have the bit mask, we can do mask searching. We can mask out bits during the search, or we can search for results that result in ASCII or in numbers or anything. And we get that basically for free. BRAMs are block RAMs, so it's dedicated resources in the FPGA that are real memory. You can implement memory in the logic, but it's pretty expensive, so that's why they added BRAMs, which is a separate memory that can be used by the logic. And there are many of these units, usually more than you need, and or at last in this project more than I needed. So they are basically free. They are there anyway, and we can just use them, and it frees up a lot of resources already by using them for the matching. Okay, the next part is communication with the FPGA. We don't want to reverse engineer for example, in this board, the 10 gigabit Ethernet switch or something, because it's pretty complicated to use. We don't need a high-speed communication when doing brute forcing, but because all we're doing is to upload some patterns and upload the key space identifiers. And yeah, so we should rather focus on reusability and cross-platform, that you could use any host to talk with the thing and don't need crazy hardware, and simplicity. So there's a nice thing, Xilinx and other FPGA vendors as well offer a thing to build some logic in the FPGA that will be part of the JTAG chain. It's called user JTAG chain on Xilinx. And since you need JTAG anyway for programming the FPGAs, you basically get a low-speed communication link for free. So that's why we're using JTAG for the communication with our core, because it's just there. We don't need to reverse more pins. We can just use it. There's an open source tool, X3SPROC, that supports many different cables and a lot of Xilinx devices. What I did was to build a Python wrapper around it to provide two simple features, which is program a bit stream and scan something through this user chain, which is this communication mechanism. So I could write my code in Python, which is much easier for me. So the idea is there's a host. The host will program the FPGAs, upload the bit stream, configure the matcher, which means uploading the patterns, and set the key prefixes for each DES unit, and then start the matcher counting up. And the DES engines will encrypt zeros with the key prefix they got plus the counter. If the matcher detects a hit, it will stop counting up, it will set a status bit. The host will at some point poll the status like once a second or even more. So, and if a match is found, it will just restart at the next key. For the distributed approach, we need a server to keep track of the work units, because I want to use several different FPGA boards, all brute forcing my key, and I don't want them all to be connected to a single machine. So we need a server to keep track of work units. We need a client that requests work units. It's a pretty simple protocol. The client will get the work unit ID, configure an FPGA to search that key space segment, and deliver the result, which is usually no key found, but sometimes it's a better result. There's some framework that just implemented this, like this Boeing framework used for CT at home and some other projects. The problem is they're pretty complicated. They're pretty optimized for doing stuff on a PC, on CPUs. Boeing, for example, is not so much optimized for doing brute force attacks. It's more optimized for having a lot of data to process. So it wasn't quite the right choice, so I just implemented a very simple framework. Okay, so let's do a live demo of this. And we just wait a week and then we have the key. that's not so much a good idea. So let's just skip some bits. We instead of matching for the full 64 bits of the ciphertext of the ciphertext, we will just match a few less bits. So basically, what we will be doing is this: we have zeros, we encrypt them with the key that we are looking for, and the result should be this hex string. Except that we don't care for the last 3 bytes because we don't want to wait a week. There's roughly 1 hit per 40 bits of key space, which means it's 1/64,000th of a real search. It will still take about 1 hour on a high-end machine. So let's do it here. I could prototype this on a $150 starter kit, FPGA kit, or any FPGA kit actually, and run it. It would run, but it would still take a few hours. So let's add some more FPGAs and run this thing. And now I need some extra time to set this up. So just excuse me for 1 minute, and then I have it working. Maybe someone can tell a joke or something, or do a lightning talk, or I don't know. Yeah, that's the problem, right? I just need to re-enable my stuff since we moved it and rebooted, and it doesn't boot automatically, so excuse this. Yeah, but not that part. Yeah, that's fine. Okay, it's all looking good, except for the DreamWorks.
What do we need to plug in?
Yeah, is it long enough? Probably not. Oh. Yeah. Okay, I was. Yeah. Okay. Is that a reasonable size? This still works, right? Okay. Okay. So, yeah, I will first initialize the server project again. I prepared this. I can show you what it actually does. It's setting up a new DeskCrack project. It says it configures the DS project using, it says that work unit is 34 bits, so this is about 2 minutes. So we get a result after a work unit completed, and I don't want to wait so long, so I scaled it down to 34 bits, which means that every 2 to the power 34 bits keys, we will get a response from the thing. I limited the key space search for 48 bits, which is still plenty enough to find something. I added a highly secure password, and I added the pattern, which we are looking for. The lower bits I don't care, so we will look for anything that encrypts, any zeros that encrypt to this pattern, except for the last 3 bytes. And now we can, the server's running in the background, I hope. Okay, so we can run the bot. So this is now the client that talks to this thing, to 3 of the bots from eBay. This is, you can see it programs the bit stream into the FPGAs. There are 9 FPGAs in this setup, so it will take about 7 seconds per FPGA to program the bit stream, and we have to wait for that. Will be done soon. Yeah. So it's actually interesting to see the power consumption of FPGAs when doing crypto operations, because usually if you calculate the power of an FPGA doing work, you assume that about 10% of your flip-flops will change in each cycle, which is a reasonable number for a CPU core or anything normal, like data processing. For crypto operations, we assume that half of our flip-flops will toggle each cycle. Okay, and that means that the power estimations are 5 times as much as you would have them if you would run some general purpose stuff at a given clock frequency, which means we actually have to add some cooling to the FPGAs. You can see they are running at 156 megahertz now. Let me make this a little bit smaller so it fits on the screen. Still not. There we go. So every third of the FPGA is running at a different clock rate simply because that's how they are wired up, and I didn't change that. So they produce quite an amount of heat and withdraw quite an amount of power already at this rate. Each board takes about 3.5 to 4 amps of 12 volts. So in total, this is about 80 watts or something, which is pretty something where you need active cooling already. You cannot compare this to running general stuff at this clock rate. Okay, anyway, it will search the key space now, and it will deliver the results to my server, and we will just keep it running for some time and come back later. The framework I was developing is called Crunchy, because it crunches numbers. You can find it here on GitHub soon, I have to say. What you find there is basically something that lets you build a brute force core for your Spartan 3A starter kit and test it and brute force some keys. And then with a single command line, you can build a bit stream that works on this machine. And you don't even need to have access to this machine. And you can give me the bit stream and I can work on your project. That's the whole idea. So if we have this 50 units of these boards, we can set them up somewhere. People can develop for them at home without having to care about the cooling of 50 of these boards. And then they can build a bit stream for the much larger unit, and because it scales up linear. So that's the nice thing about brute forcing. It scales incredibly simple. The way this is done, so this Crunchy framework is pretty small actually. It provides some wrappers around your logic that make sure that you can run the same HDL or the same cores on your starter kit or on some random FPGA as you could run on the huge device. So there's a definition of a board, which is basically for example, the Spartan 3A starter kit or this thing or some other boards. So you have a definition of a board that, I will just explain what it includes. We have a definition of a project, for example, DES crack, that contains the actual HDL to build the bit stream, like the DES core, the matcher, some metadata. There's some piece of thing that runs on the server that configures the work units, for example, the number of work units we have and how to make sure that how to validate them and so on. And something for the client, which actually communicates with the cores that it just built. And then there are parameters that configure a project to run on a board. For example, the number of cores is something you have to change. If on a small FPGA, you want to have 1 core. On a big FPGA, you want to have 6 cores or 10 cores. And you want to reconfigure that. So a board support provides top-level HDL that, for example, talks with the LEDs or something. It's really not much. It's in total 100 lines of code. You can add a support for a specific board if you have the pinout in half an hour maybe. And the board defines interfaces that projects can use, like very simple interfaces like clock, which is a single line where clock is coming, or LEDs, which is a single line where you want to display status. So you can see it blinking, maybe. No, you can later see it blinking, and actually it doesn't, yeah, it blinks. So you can see it blinking, and there's like this user JTAG thing. So yeah, as I said, it's a really tiny piece of code that will allow you to run any project code that somebody else developed on your board. So yeah, if we see this here, there's a fpga starter, and it has a slot for a project that offers the reset interface, which is the reset line, a clock interface, and the user JTAG interface. So 3 simple interfaces here. And any project that uses these interfaces can just plug into this slot. The project provides HDL that can be configured depending on the needs. For example, the number of cores is configurable. The project also provides client code that uses the abstracted board interface, which is the scan user thing, to talk to the FPGA. So if you want to use, I use a simple FTDI-based JTAG cable, but if you want to use a proprietary JTAG interface, you could just rewrite the abstracted board, or the actual interface of the board to provide the same interface, and then other projects can use that code. And there's some server code, as I said, to configure the parameters. This is how the actual project here looks like. We have, for number of cores equals 4, for example, we have 4 desk cores. They all deliver the result to the matcher. The matcher controls the counter, the lower bits of the key, and they are all chained up in this user JTAG chain, so we can talk to them. If you have a board, or if you choose a board, a project, and the parameters to fit the project into the board, you can build a bit stream. And a bit stream is what you load on the FPGA. The server project, the server contains a definition of the project it's running, and it lists supported boards with their parameters, and it distributes bit streams. So you don't have to build the bit stream on your own. You can just attach to a server, and if the server has a definition for your board, you can use that bit stream that was already pre-built. You can also supply your own ones if you have a custom FPGA board. And yeah, the code, the client code that runs, that talks to the FPGAs, knows how to talk to your board then. So the idea is really you prototype your brute forcer on a small FPGA and you run it on a big cluster, which is nice if you have access to a big cluster. The alternative is to just run it on a lot of devices. So some consumer hardware have FPGAs, like for example the 3G femtocells. If you look at them, they have a pretty large FPGA on them. Another example is this satellite receiver. I was working on this project a while ago, that's why I'm using it. It's a great receiver, by the way, but that's not why I have it here. The reason why I have it here is because it has an FPGA that's used normally for muxing data streams between the tuners to the SoC decoder. It's a Spartan 3E500, so it's not so huge, but it's still useful if you have a lot of them. JTAG is available as a GPIO, so what we can do is to run the same project that we run on the big device on a Dreambox. And we can build something that Dreambox users can install to use their FPGA processing time, for example, in standby mode, similar to what distributed net was doing. Just we do it for FPGAs. And it is much more effective to do this on FPGAs, also power-wise. So this can be an interesting thing if there are a large number of devices out there that you could get. So I was supposed to do a demo here. I will do the demo later because it might take some time to get this set up again. Possible improvements for this project. You can work on the DES cores, of course. The Copacabana project has their cores optimized for their architecture. I just used the open cores DES core. We have some work in progress here. You can add, of course, other number crunching projects. We could add more communication methods if JTAG is not available, or support for non-Xilinx devices, all of that. On the client-server side, I said it's pretty simple currently. What I would like to see is that you can subscribe to a project feed and say, hey, I want to work on any project that some person finds interesting, some person I trust finds interesting, and then it will automatically take part in an interesting project that that person announced. Something like that. So you don't have to reconfigure your device every time a project finished. So you just, it will just poll if there's work to do and do the work. Also, I haven't implemented any kind of security except for my top secret password. Especially there's no anti-cheating security, so you can just grab 100,000 work units and supply them as work done and nobody will notice. There's some interesting method to to validate responses, and that needs to be implemented if you're using this framework outside of a trusted environment. Same goes into the other direction, bitstream authentication. You don't want to run a random bitstream on your FPGA bot because the bitstream could do very bad things. So you want to have some authentication here. But yeah. Oh, results, right. So we had this running, and let's see if it found something. So remember, on a PC, we would expect it to find 1 key per hour about. So let's see what it got here. So we can ask for the status. And then, it found already a number of keys that all match the given ciphertext. So let's try one of them. Let's try just encrypting zeros with any of these keys and look for what the results are looking like. And if everything worked, which I hope so, then it should give the pattern that we have been looking for. So I will just use whatever. The first one, and encrypt, typing is difficult, encrypting 8 zeros with it, and I want to show this hex string. And we see we got our pattern here. We got 32, 37, 43, 33, which is 27, 33, and the 0. The last 3 bytes are filled with random data. So if we take another key that it found, this one, we will see that the last bytes differ, of course. I hope you can read this. I can make it larger. It's too much. So you can see that it actually worked. It just found, while I was doing the talk here, it found some keys that match our pattern. And of course, this is just a 40-bit key search, but it's still pretty impressive how many keys how many hits we got. We can see how many work units is already finished. So a work unit was 2 to the power of 34 bits. And we can see that it already finished 306 work units. Which is 1.8% of our reduced key space, in just a few minutes here. So, yeah. Okay, this was obviously a demo result, but it was calculated live on this device, so there was no cheating involved. If you don't believe me, you can give me another text to look for, and I will brute force your partial key. But this is a boring result because, well, it's a magic number maybe, but it doesn't help us solving our mystery. So while I was implementing this, I let it run for a few days, basically, running my test code. And some days I was looking at the result, and I found this. I found actually a key that was not one of my test keys. And if you look at this, this is a pretty simple key, right? It's 002244. So if you look at it in binary, it starts with actually 11 zeros. No, 10 zeros, whatever. Many zeros. So that, since I started the key search at 0 upwards, I found it pretty early. So I found it in the 276th work unit, which is after about 5 hours or something. So again, so here's the problem. If this is a 56-bit key space, and you choose a bad key, and keys should be random, always random. Don't try to set the first 10 bits, or I will crack it as well by just starting at the upper. So choose random keys. If you don't do that, you will lose important bits of the key space. And in this case, I have again my standard FPGA set up 9 units, and it just required me 1.9 hours if I do the math to get the key, because the key is so bad. So it actually brute forced the real unknown key already, pretty simple key, but I wouldn't have guessed. So if we decrypt our patterns, we should see some match here. So we see that if we decrypt these are the 8 patterns again that I've talked before. So the marked here are the byte reversed C1 and the byte reversed C2. So we actually see that they decrypt to all zeros and all FF. So we found the key. We found the non-negated key, by the way. So the desk complementation thing didn't really help, but we found the key. And it was C1 was all 0, it was byte reversed. Lucky that we looked for that. So if we decrypt the firmware now, we can see some strings. This is actually part of the security protocol that this device talks with the game authentication dongle. So I could finally, after like literally 2 years, I could solve this mystery by brute forcing a DES key. So. Okay, thank you. So if anyone else has keys to brute force, I mean, if they are DES, feel free to give me the ciphertext and the pairs. If you have any questions, I will be down in the Hack Center the next 2 days or 2.5 days. If you want to build support for your FPGA board, ask me. It's really not a big deal. And yeah, keep on hacking.
Thank you, Felix.